Good morning. In this fourth module of electronics, in modules 1, 2, 3, I try to explain the formation of P type, N type material and its junction. Now, after formation of junction, the most important concept is how the charge carriers are moving inside the P N junction, that is flow of the charge carriers in P N junction. Well, there are two type of charge carriers, one is electron, other is hole. So, the electron is negatively charged, but hole is neutral. So, due to the motion of electron, the empty place is there and that empty place is termed as hole. So, for the movement of charge carrier, there must be external energy and that external energy applied through the external potential, and that process of applying external potential across the P N junction is termed as biasing. So, biasing P N junction, biasing across the junction. Biasing is the process of the application of external potential. Mind it, this is external potential that we have to apply across the P N junction so that it moderate means it accelerate the movement of charge carrier or it deaccelerate the movement of charge carrier. So, the word is it moderate the movement. It moderates the movement of the charge carriers, that is holes and electrons. For this, we have to understand the energy level of P N junction. P N junction. The external potential or energy modified the potential barrier that is either increase or decrease for the charge carriers. So, how to modify? In order to understand in modification, we have to concentrate about the energy level diagram. The energy level diagram of P N junction is a combined energy level of P type and N type semiconductor. If we focus this only in P type semiconductor, so we have this much diagram is a P type semiconductor. Means this one is a valence band, this one is a conduction band, EVP, ECP, and due to the P type semiconductor, that is trivalent impurity doped. So, there is availability of holes in the valence band. So, these are the holes inside the valence band. So, what happened? There is a lowering of conduction band. Now, in this case what happened? N type semiconductor, this is valence energy band N type, this is conduction energy band. When pentavalent impurity doped, this valence band rises. So, it is EFN, Fermi-Energy of this M. Now, as the P N junction formed, this energy level EFP, this energy level aligned with the energy of Fermi-Energy level in N type semiconductor. And due to this alignment, there is a slightly development of this potential, and this development of this potential means the potential difference, that is you have this one, this value or this value. This development of the potential is due to the diffusion of charge carriers, that is electron from n type to p type. When electron left from n type and completely accommodate in n type, then here it is positive charges and here it is negative charges, and these two is, here it is, as we have said, this is the width of p type, this is width of n type. So, it is CDR region and the potential developed is Vj. This one is the potential developed across the CDR region. And so, what we have? We have motion of charge carrier. First is diffusion across the junction only, and second is drift inside the extrinsic semiconductor. Now, motion means there are two type of charge carriers movement inside the semiconductor across the junction due to the density difference. So, diffusion across the junction only. This is very important concept, because several objective type questions are made on the basis of this P N junction. What kind of the charge carrier moving across the junction? It is diffusion, drift, both, none, something like this. Or which kind of the charge carrier moving inside the crystal? Then it is drift, the inside the semiconductor. So, there is here it is the density, it is due to the density, and here due to the field. When there is external field, then there is a drift motion, and the external field means applying the biasing. So, now with this energy difference and these two type of the motion of charge carriers, that is diffusion and drift. Now, we have well versed with the concept of diffusion, that is very important in this place also. How? The concept of drift velocity, as we have studied in our previous classes, that is Ohm's law. Ohm's law, we just want to sketch Ohm's law in a quick manner. Suppose this is a conductor, here it is conductor, say copper, and this is the A, that is area of cross section, and here it is the length of the conductor, and the charged electron, this is free electron moving with the velocity Vd, that is Vd drift velocity, having n number of free charge inside the conductor and number of free electron per unit volume. In the conductor. So, the total number of charge free electrons the total number of charge carriers, that is electron, is say n, capital N, and this is small n into volume, and this small a into volume is A L, that is A is the area of cross section, A is the length, volume, then charge q is equal to this n into E, that is small n, this is A L into this is electronic charge, E is electronic charge, that is 1.6 into 10 to the power minus 19 coulomb C. Now, current, if you want to find the current, so current I is equal to Q by T, this is N A L E by T. Now, this time can be calculated as T as L by V D, L by V D, length upon velocity, because velocity is equal to L by T. So, this is, that is N A L E bar, this is T L upon V D. So, this L cancel, N A E bar into V D is the current. So, this is the current, and this current can generate the current density. That current density is, the current density is expressed J, this J is equal to I upon A, this I from that particular equation, small n A E V D upon A. So, this A cancel, so N E V D. So, J is equal to N E V D. This V D is drift velocity, can be expressed in terms of mobility. Mobility is mu and defined as mu is equal to V D by E, V D, that is drift velocity, upon electric field. So, V D is equal to mu into E, V D is equal to mu into E. So, this V D drift velocity expression can be substituted. So, the current density J is equal to N E and this mu E. In place of this V D, we can substitute this value as. So, what we find, this is N E mu E is J, mu is J, or we also have J into E, where this sigma J is equal to sigma into E, sigma is conductivity conductivity of conductor, conductivity of conductor. So, by comparing these two expressions, the conductivity is conductivity sigma is equal to n e mu. Conductivity sigma is equal to n e mu, and we also have resistivity rho. This rho is equal to 1 by sigma, that is 1 upon n e mu. This is 1, this is 1 upon a. So, this is from the previous class, that is from 12th Ohm's law. We have from the, this is also known as Ohm's law. This is also known as Ohm's law. So, this basic concept of the conductor Ohm's law can be applied in case of the P N junction. In case of P N junction, we have to in case of P N junction, we have the terms as, this is P, this is N. So, in case of P N junction, this N number of charge carriers in N type. So, this is number of charge carriers in N type, and mu e mobility of electron, mobility of electron. Similarly, we have Np, the number of holes in P type. Np is number of holes in P type, and mu p is mobility of holes. So, on the basis of these two, we can have another important concept for conductivity is J, this is J n, current density. So, this J n can be written as n suffix n, that is number of charge carriers across N type, then electronic charge same, then mu e mobility of electron, and then here it is electric field. Similarly, this is P, that is current density in P type. So, this J suffix P is equal to N P E, this is E electronic charge, mu P and E. So, these two are the current density of charge carriers. This is N type and this is P type. The total current density of P N junction diode is J, that is J is equal to Jp plus Jn. This can be written as Jp plus minus Jn. because the motion of electron is opposite to the motion of hole. So, if we are getting this 2 negative, so we will get it. So, substituting the value J p is N p E mu p E, and here it is J n N E mu n E. So, what we find, you take this E comma, then N p mu p plus N mu E of E is the current density is in the P N junction. Or from this current density, we can also have the conductivity. We can also have the conductivity, and for that conductivity, if we collect the data set for this is germanium and here it is silica. So, first data set, property first is atomic number 32 and this is 14. Second is you can take this n. So, 2.5 into 10 to the power 12 per cc, and here it is 1.5 into 10 to the power 10 per cc, here it is per cc. Then the mu n is in terms of the mobility, in terms of centimeter square voltage inverse and second inverse, the unit is. So, this value is 3600 for this, and here it is 1300 mu n for electrons, and electrons for hole this one is 1400 and here it is 500. So, on the basis of this data set, if you calculate the numerical part, example, find out the resistivity of germanium at room temperature, that is 300 Kelvin. Solution: resistivity is defined as inverse of conductivity. So, conductivity sigma can be expressed as sigma is equal to, this part is E, this is N p mu p plus N mu E of this part, E n p and mu p. So, we have the value, this is N and this is the mu. So, we can take this value for germanium. for germanium, we take the value of Np is equal to Ne is equal to 2.5 into 10 to the power 13 per cc. So, conductivity can be, conductivity sigma is equal to E n mu E plus mu p, mu E plus this n is, this is your n. So, substituting the values, we have sigma is this electron, the charge carrier 1.6 into 10 to the power minus 19 C, n is 2.5 into 10 to the power 13 per cc, mu is 3600 plus mu p is, this is mobility of hole is 1400. So, we find this 1.6 multiply with 2.5. So, this value is 4.0, 1.6 multiply 2.5. So, it is 4.0 and power, here it is 10 to the power minus 19 and here it is 10 to the power plus 13. This is plus 13. So, we have this is 10 to the power minus 6 and inside the bracket this is 3600, 1400. So, this is 5000, this is 5000. So, what we have 4 into 4.0 into 10 to the power minus 6 into 5 into 10 to the power plus 3. So, this 4.0 and this is 5, this is 20 and this is 10 to the power minus 6 and 10 to the power plus 3, that is 10 to the power minus 3. So, this is 0.02, this is 0.02 will be the value of sigma, the value of sigma. Now, in the question is resistivity. In the question there is resistivity, that is resistivity is 1 upon conductivity, that is 1 upon, this is 0.02, 1 upon 0.02. So, 1 upon 0.02 is nothing but 100 by 2, which is 50. This is 50 ohm centimeter. So, this sigma is equal to 50 ohm centimeter be the answer, that is resistivity of germanium, and that is why it is a semiconductor material. Now, we have these two values, n of electrons, this value n of number of holes and this is the number of charge carriers. So, on the basis of these two parameters, we can also have one important law, and this law is known as law of mass action. Law of mass action. This law of mass action is Ni. law of mass action is Ni is intrinsic semiconductor conductivity. So, it states as Ni whole square is equal to N of P, and this is N of N, N of P into N of N, where Ni is charge carrier, electrons per unit volume, that is approximately 10 to the power 10 per cc, that is 10 to the power 10 per cc in semiconductor. In the semiconductor, while it is 10 to the power 28, we have this one is Ni is equal to 10 to the power 28 per cc in conductor, and 10 to the power Ni is 10 to the power 5 per cc in insulator. So, what we find, this Ni for conductor is greater than Ni of semiconductor is greater than Ni of insulator. So, what we find for this particular question, note, we can have this note what is the value of Np in germanium in above question. So, Np is equal to what? Np is equal to this Np we have to find. This Np is equal to Ni square upon N small n. So, Ni square, this is 10 to the power 10 whole square, and this is 2.5 into 10 to the power 13. This is 2.5 into 10 to the power 13. So, this is 10 to the power 20 upon 2.5 into 10 to the power 13. So, solving this is 1 by 2.5, 1 by 2.5 is 4, this is 0.4 into 10 to the power, this is 7, 1 by 2 is 5, this is 0.5, so 10 to the power 7, this is 4 into 10 to the power 6 per cc. This is your N of P. It means the number of hole. This means number of holes. So, number of electrons are 2.5 into 10 to the power 13, and number of holes is 4.4 into 10 to the power 6. So, number of holes are less than the number of electrons. It means this is N type crystal. The germanium is N type crystal, where the doping concentration of pentavalent, there is a pentavalent impurity in the crystal. So, this one is the current density, conductivity and resistivity of the circuit. Now, this is all about the module, and in the next lecture I would like to discuss about the type of biasing, that is forward bias and reverse bias, and then VI characteristic, that is diode current. Thank you.